Hello everyone. In this session, I'm going to solve question number 31 to question number 40 regarding the DC machines topic from the textbook V.K. Mehta. This is an objective question textbook. Okay. So let's take up the question number 31 here. Question number 31 says that a 6-pole lap-wound generator has 300 conductors. The EMF induced per conductor being 5 volt. The generated voltage of the generator is dash. Okay, so they are given 4 options here, and meanwhile they have also mentioned some of the given data here. There are 6 poles, so I have just taken it, the number of poles are 6, and they are given that number of conductors are 300. Okay, and they mentioned that the EMF induced per conductor is 5 volts. So I have mentioned here E is equal to 5 volt. Small e indicates that is EMF induced per volt per conductor, sorry, whereas capital E is an EMF induced in the system. So 5 volt for Z equal to 1, it's nothing but for one conductor. Now I want to find out total EMF induced in the generator, that is E is equal to EMF induced in single conductor into EMF induced in the parallel path. So one thing you need to understand here, that is, look at this part. In this given question, they have mentioned that there are 6 poles. So the parallel paths for lap wound will be equal to the number of poles. So based on that, we can say the parallel paths are going to be 6. So in general, the mistake what student will do is, for one conductor we have 5 volt, means for 300 conductors it will be 300 into 5, 1500 volt. That will be the mistake generally done by the student in a hurry. But you need to understand that in a machine, when they are talking about a generator or a machine, the voltage induced is nothing but that is the voltage induced in one parallel path. There are totally 6 parallel paths given in the question. Now look at this example. There are 4 parallel paths here. There are 4 poles, 1, 2, 3, 4. So parallel paths will also be 4. So based on the parallel paths, we got the numbers here. We got the brushes here. 1, 2, 3, 4. But you may be having 4 brushes, but whatever the voltage we are collecting at the end will be across only 2 terminals. Means all these, both the positive terminals will be connected, shorted together and taken as one terminal, and both negative terminals will be shorted together and taken as another terminal. It means whatever the voltage we have at this brush, because of one parallel path, will be the same voltage we have at this brush also. So each parallel path will have a same voltage, as you all know that in parallel the voltage will remain same. So according to this question, as they have asked EMF generated in a generator, means you need to find out the EMF generated in a one parallel path. So according to that, I have mentioned here that number of conductors per parallel path will be equal to Z by A. You should not calculate it for overall conductors. You should calculate it for the conductors which we have in that one parallel path. So Z by A is nothing but 300 by P, because A is equal to P. So 300 by 6, and that result is 50. The number of conductors in one parallel path is 50. So now we can say that EMF induced in a generator in one parallel path is 5 into 50. That is EMF induced in one conductor into EMF induced in one parallel path. That will be 250 volt. So the answer for this given question will be option 4, that is 250 volt. I hope I made it very clear about the concept here. Don't answer by just looking into the question blindly. See, 300 into 5500, even that option is mentioned here, but that is wrong answer. Because one simple agenda you understand here, in a generator you may be having 10 parallel paths. If it is a lap wound, you will have 10 brushes, but finally we get 2 terminals out of it. So from each parallel path you will get the same voltage, right? So you need to find out the voltage per parallel path. Means for that you need to know what is the number of conductors in that parallel path. Don't consider all the conductors, overall conductors. Okay. So based on that, you got a question and you got an answer as 250 volt. Option 4 is the answer. Right. Now let's move for the second question here. Question number 32 says that for the same rating of DC machine has dash and AC machine. So they are comparing DC and AC machine here. The same weight as an AC machine, means the DC machine has the same weight as an AC machine, or more weight, less weight, or none of the above. So very simple question it is. AC machine and DC machine, whenever we compare, the parts almost remain same, but only one change in DC machine is the commutator segments will be included. So when we are including an additional element into a DC machine, definitely the weight is going to increase. So we can say that the answer for this question will be option 2, that is more weight than the AC machine. Right. Now let's move for the question number 33. The field winding of a DC shunt machine usually carries dash of the rated current of machine. Okay, so in a DC shunt machine, field winding will be across the armature, and we need most of the current into the armature. Okay, so what we do is the design will be in such a case that the shunt field winding what we have, its resistance will be very high, such that the current flowing through that shunt field winding will be small. And if we reduce the current through the DC shunt field winding, then the flux in that shunt field winding will also be reduced. And if I reduce this flux, the speed will increase, because we know that N is proportional to EB by phi. So N is inversely proportional to flux. Okay, so we can easily understand that the current flowing in the shunt machine or field winding of a shunt machine has to be low. So it has to be low in the sense the option 1, that is 2% to 5% of the current will be flowing in the shunt machine. So I have already clarified it that why it should be low. If it is low, then the speed will be high. Okay, that is also one logical point you need to think here before answering for such questions. Okay, and don't go for this less than 0.5%. Even that much of low current is also not possible over there. So 2 to 5% will be the answer for that. I hope you are getting the points here. If it is clear and if you want to have similar kind of videos, then you just like it and comment it in a box regarding that. Now let's move for the question number 34. A separately excited DC generator is not used because dash. Okay, so in this picture you can look at here, we have a separately excited DC machine here. So separately excited in the sense name itself indicates the field winding is going to be excited with a separate DC supply. So we need to use another supply, DC supply, to excite the field winding. That is the major problem in this separately excited DC generator. So that because of this reason, this separately excited DC generator is not used. So option 2 will be the answer for this question. Separate DC source is required for field current or for field circuit. Question number 35. A DC compound generator having full load terminal voltage equal to the no load voltage is called dash generator. Okay, they are talking about the compound generator here. So compound generator can be given in 3 different ranges, that is over compounded, flat compounded and under compounded, and we are going to name this according to the variation of the terminal voltage with respect to the current. So here you can see at full load current, you can look at the graph ABC curves here. At full load current, if the voltage if it is greater than the terminal voltage, see at no load current this is the terminal voltage, and at full load current this is what the terminal voltage is. So look at this over compounded. In over compounded what happens, the voltage is getting increased, it is more than the terminal voltage at no load. Okay, at no load the terminal voltage is less, whereas at the full load the terminal voltage is high. If the terminal voltage is high at full load, then it is called over compounded. If the terminal voltage is same as the no load voltage, then it is called flat compounded. If the terminal voltage is less than the no load voltage, then it is called under compounded. So for this question, the option 3, that is flat compounded, will be the answer. Okay, so I also explained what is an under compounded and over compounded concept here. So even though they make the changes in the question, you can answer it easily. Now let's move for the another question. Question number 36. There, the main drawback of DC shunt generator is that dash. So looking into the characteristics, you can understand what is the main drawback here is. So before answering all these things, theoretically you need to be very strong with the characteristics of a machine, sir. See here, the main drawback of this shunt generator will be looking this is the main drawback here. Look at this voltage, that is the terminal voltage. At no load condition, the voltage is high. When we go on increasing the load current, as the load current increases, the terminal voltage is decreasing and it is almost, there is a huge drop in the terminal voltage. Okay, right. So the terminal voltage drops considerably with the load variation, with load increasing, right? That is the reason why shunt generators are generally not used widely. That is a major drawback we have with the shunt generator. But that, what is the advantage of shunt generator? Shunt generator can give you the constant operation, constant speed. That's an advantage. But the voltage will be dropped. Terminal voltage is going to reduce with increasing load. That's the drawback. So question number 37 here, DC machines which are subjected to abrupt changes of load are provided with dash. Okay, so there is a DC machine and it is having a variations in the load. Abrupt changes is nothing but more variations of load. Then what has to be done? Whether we should go for an interpole windings, compensating, equalizers or copper brushes. See here the copper brushes option will not come into picture because copper brushes are used to collect the current from the commutator segments. Okay, whereas here they are talking about the variations in the load, so that will affect the armature. So in when we vary the load in armature, what happens? We get some additional current. Okay, to overcome that additional current we need to maintain some constant flux in this, in between stator and rotor. Look at this picture. In this air gap we need to maintain the constant flux. So because of the variation in the load there will be variation in the flux developed. So that increased flux has to be reduced or has to be counter attacked by the interpoles. So interpoles are used to what we can say, to protect the system, to protect the DC machine from the variations of the load. Whereas compensating windings, you can look at here, I have also shown compensating windings. See plus these are the compensating windings. These compensating windings are placed in the face of the pole shoe. Okay, in the face of the pole, and these are used to reduce the spark or to vary the it is used to reduce the spark and have the smooth commutating system. And even equalizers are used in the lap windings, especially it is used for the lap windings to balance the voltage, to reduce the flowing current in the armature. Okay, so for this question option will be the interpole windings. So these are the windings used to overcome the changes of load. Okay, now let's move for the question number 38. In this figure shows the external characteristic of dash generator. So they have given a characteristics curve. You need to answer which machine it is representing. Okay, so here the terminal voltage, look at this, what's happening here is the terminal voltage at the no load condition is high, whereas when as we go on increasing the load current, the voltage is reduced drastically. And this drop is because of some drops has been written in 1, 2, 3 and 2 is empty because we have another question related to question point 2. Okay, so IARA is nothing more than voltage drop in the armature and weakened field. So because of the shunt field weakening there is a voltage drop here. Sorry, so here itself I have answered you. See, this resembles the characteristics of a shunt field or shunt winding machines. So we can say the answer for this question is option 4, that is shunt. It is giving an information of shunt generator because in shunt generator the terminal voltage is going to reduce as the load on increases, and it is reducing here. Right, now question number 39 is relevant to this question, this graph, wherein the 2 here, the 2 is not mentioned here. Drop due to second point is not mentioned. So what is that second? That is the question here. Referring to previous figure, the voltage drop at number 2 is due to dash. So generally what are the different types of voltages drop we get here is, we have an armature voltage drop, we have a field weakening voltage drop, and also we will have an armature reaction. So question number, the point 2 is highlighting the armature reaction. That is, because of the armature reaction there will be voltage drop in the shunt machine also. So option 2 will be the answer for this question. Now let's move for the last question for today's session. That is, in the given figure shows the external characteristics of a dash generator. So this characteristics is representing which generator? See, the terminal voltage is 0 when the load is 0, right? And when load increases, the terminal voltage is also going on increasing, right? So this is representing a characteristic of a series generator. I have already shown you the shunt generator characteristics, and also compound generator characteristic was also mentioned with you. Okay, so in that compound generator we will have almost over compound, under compound and flat compound. Now this is the only left out question option is series, and this is in series. What happens, the voltage is going to increase gradually when we increase the load current. So option 3 will be the answer for this question. And also one thing you need to remember, these are all about external characteristics. If you consider the series motor, then the speed of the series motor will be very high when there is no load condition. So that is the reason why we always say that series motors has to be started with the load. If you start without a load, then the speed will be drastically high, so that the machine may get out of the foundation, it may come out of the foundation. So that's the major problem we'll be having in series machine. So care has to be taken that the series machine has to be started with the load. You cannot start it without a load. That's the point. Okay, I hope this session is very helpful for you guys, and if you are catching the points and if you are able to understand the concepts here easily, then please press the like button. Don't forget to subscribe to my channel so that you can get the notifications whenever I release a new video. Thank you.